Sure to introduce Julia. Did her PhD in Universidad Autónoma de Madrid, focusing more on plants and ethnobotany, and now she's working on time series and insects. So,
thank you, Nacho, and thank you also the organization of the EBD seminars for having me and organizing everything. So indeed, I'm Julia. Some of you might know me or not. I'm in the Green Building, and I've been here for 1 year and a half, working mainly on pollinator trends in general. And what I'm going to talk about here is about these population trends through 3 edges that would be from monitoring, modeling, and prediction. And we will look at the different outcomes it will get. So I will start talking with about insect dynamics in general, a bit of introduction theory. Then I will talk about these novel monitoring techniques that we are implementing. Then about the identification of uncertainties when developing models, temporal models. And then I will shortly describe forecasting tool that we have been developing as well. So first, for the insect dynamics, you might all know that insects are on a huge debate right now about their decline. The decline might be affecting their abundance, the diversity, leading even to species homogenization, and getting to the loss of the ecosystem services such as pollination and decomposition, etc. And what we have here and what we are missing is a good model estimate to detect the changes of these insects because they are fast-lived, and this has led to a big debate whether they are in a huge decline or we just don't know what is happening. We cannot know. We don't know enough about models to get this answer right. And this is because data are usually too patchy, they are geographically biased, or they join aggregated metrics. And not only because of how the data are in place, but also because of the nature of the insects themselves, that they are known for having this population that is annually renewed each year, that they have non-monotonous variation, very dependent on the environmental variables, and also relying or not on the trends that we see depend a lot on the sampling frequency, the error, and the year effect, and the years we are accounting for those data. So given all this, we are still lacking a robust, large-scale implementation of models. And this is what we want to get right here. We want to get these good estimates, not only because it's important, but now because even we have to reverse the decline of pollination by law. I don't know if you are aware of the nature restoration law that has been determined in the last years, and that has many objectives, and one of those is to reverse the decline of population of pollinators. And it is curious that is for all the targets of this law, pollinators is the only group that appears, so it's very important. They have given it a huge role in this nature restoration law. So regarding pollinators, what the law says is that we need in Europe to reverse this decline with a pollinator scheme that has been developed and will take place next year in 2027. So given that we need to recover pollinators now by law, but that these laws has to be reversed in 2020 and 2030, we only have 3 years of that data to get this change in the population trends. So it's primordial that we get right the monitoring and modeling. It's something that we really need to take into account. And this is where the antenna project comes in place. This biodiversity project, and what it wants to mainly address is these gaps in monitoring and address it through these novel techniques. So the project itself looks at novel techniques in the field that can be applied, also in the lab, to integrative modeling and to large-scale implementation to predict, in order to predict population trends. I will look at it a bit of the three of them. I will present work that is not mine, that is the whole project. But like this, you get an idea of what we have been doing. I will start with the novel monitoring techniques that have been tested in the field in Doñana last year during the spring season. And this field testing includes many different novel and traditional techniques. These where we have tried pan traps and also transects, and also we have tried these camera traps for insects that I will explain a bit in depth here. So as in the field, we try this pan trap versus camera traps, and in the lab, this manual sorting and species identification compared with automatic identification and detection. So we don't have the results yet, but I will explain a bit what we have found just comparing pan traps and transects. We know that in general, pan traps are more biased towards Diptera, Coleoptera, and Hemiptera, that they might have difference in the color of the pan trap. And that in general they are good because they have this high temporal coverage. We leave them there during the whole day of fieldwork, and then we collect what we have found. Also, as a concept that we have is that is an aggressive method because it kills all the pollinators, and also it gets a less diversity of bees compared, for example, with the transects that we really have a good in the data. We also can see that for bees and syrphys is much more efficient as a method. We can also get the plant-pollinator interaction out of this data that with the pan traps we'll use it. And it depends on the expert knowledge. So it can be biased through the knowledge of the one who is making the transect. This is a bit the cone. It's not as homogeneous as the pan trap. And it's temporally biased. So whenever is there, opens the window, whatever is there is catched. And this was compared with the Diopsis, that is a machine that was developed in Naturalis and is a huge machine. I don't know if you know it is kind of like this. And it has a screen, yellow screen, UV, and a camera on top. And then everything that is detected that is an insect is then pictured. And this is the kind of pictures that it takes. And is quite interesting because the pictures are automatically uploaded to the cloud, and you can look at the results in your phone in the moment. And so you can more or less monitorize what is happening. But it's quite heavy, for example, from bringing it to the field. And we have compared this method to another one that has been developed in Aarhus University. That is a small camera that is more or less this size, that also has this solar panel. And it has, instead of the flat yellow platform, it has these flowers, artificial flowers. And then it is not that it detects when there is an insect, but it takes one picture per minute. So whatever is there is taken or not. And this is less complex than having this algorithm for automatic detection. So it is quite cheap. It's less than 200 euros. So then it makes like a better version, perhaps, of this camera can be ready for city science quite soon, for example. And then it has this SD card, but we left both of them in the field for 2 months, 2 whole months, and we just had to go once to change the SD cards. And this happened in the field. I don't have the results of the comparison, but as soon as we have it, I guess it will be widespread. Then I will explain which are the methods that we compare in the lab. So we compare the manual sorting and the identification of an expert taxonomist. In our case, is Curro Molina. And what we want to see is the difference with automatic detection, that this is another machine that has been developed, that is a EthnoScan. It's a scanner with like a hole in the middle where a Petri fits, and then you scan it, and then you get those pictures. And with these pictures, I don't know if the micro is correct, but with those pictures, you even if they are one-sided, it can be then passed through an algorithm to detect the insects, and is less efficient than other machines that have been developed that has, for example, this is a biodiscover, that it takes the whole body while going down from in a liquid environment. Then it takes all the 3D of the insect, but still is quite good, because then with this algorithm that has been developed that is called flatback, then it gets automatically detected for both the scanner and the pictures, and then it can be automatically also identified with BioClip 2 that has been released not that long ago, and this has been done to the order level. And here you can see the folders and the amount of pictures you have per folder. So you can see that Hymenoptera is 4,000 pictures, for example, but Diptera is almost 20,000 pictures. So it has a bit of behavior of a pan trap. So like this, like preliminary, we can see that perhaps the flowers work a bit like the behavior of a pan trap, but it's not aggressive. We cannot get farther than order with this algorithm, because one is to the species level is not reliable, but to the and also because it has been fed with pictures that are not from our latitudes and from this hotspot of pollinators. So they are the biggest amount of pictures is from the US. So then it's perhaps to the order or even to family, you can trust it, but no farther than this. So as a conclusion of this first part, we can say that the novel methods are good because the taxonomic and the geographic and the temporal coverage is higher. In general, you can live 2 months something to just get data. But then we need to annotate to train. The taxonomic resolution is not good. Well, it cannot be at least good for now. Then it's not user friendly. It has high cost. It demands energy, etc. So it's a joint work between novel and model methods, which will be perhaps optimal, because you can at least get your data roughly. You can get the abundance of all the insects that are there with camera trap, and then to the detail you can look at the species, if the species have been changed species composition. For that, you really need to be careful and identify to the species level with detail. Okay, so that would be the first part about novel methods. And now I will explain a bit what we have been doing more in detail about modeling. So what we have tried, this is something we have developed with Francois Duchesne, that I don't know if you know him, but he was here as a postdoc last year. And we have developed this out of thinking and getting the ideas of, okay, how we can measure uncertainty, how we can know when when can we trust and when can we not trust. So this was our question: how robust are pollination or population trends in general? So we want to know, to address that question, what we did, it was, okay, how the trends are actually affected by different time series characteristics. So we have duration, that is just how long are we doing monitoring. Temporal trend, so the slope. We have the interannual variability, the stochasticity. So how the variation is from one year to the other due to stochasticity. And temporal autocorrelation is with how much are we depending on the conditions of last year. So we have all these time series characteristics, and what we did, it was, okay, let's take all these and model, simulate time series abundances. So for you to see more or less how the our simulation look like, here we will have something that has a low stochasticity or interannual variability and a negative autocorrelation. Negative autocorrelation creates this pattern of one, the next one is on the opposite side than the following one. So it gets this this like zigzag pattern. And then we have low negative. So you can see that it has this zigzag 0 that is a bit more random, and positive, and it is, we are going to see 1 point followed by the previous one. This is when we can only see it like this when the trend is 0. If not, well. And then we have here the model. So this was what we have simulated, and this is what we obtained from the slope we obtained from the model. And then we see how much difference are between those. When we increase our variability, then we see that our error clearly increases. And when this is the trend that follows with negative autocorrelation and then positive autocorrelation, the points are more related to the previous one. This is what we did, but not only for these 3 cases, but we did it for 15 different values of interannual variability from 0. So very, very constant to very stochastic. Duration from 3 years to 40. Autocorrelation from negative to positive. And temporal trends, 51 different values from minus 25% change per year to plus 25. So all the range. This gave, and out of all these combinations, we simulated these trends. And this gave, with 100 replicate combination, 14 million models. That what we did afterwards, it was to analyze each of these models with a GLM and obtain the same time series characteristics. So we could compare, okay, we have what we know that is real because it's simulated, and then we know what we obtained from the models. And let's compare those to see where are the errors. And we have 6 different types of errors. We have the slope estimation error, that is just 1 minus the other in absolute terms. We have the statistical powers. How can we trust that a certain train is actually found? And false positive, that would be, okay, we are supposed to find any train and actually any trend, and actually we are finding it. So yeah, the false positive classic. Then we also have the time M, that is in magnitude terms, how it's similar to the slope, but in other units. Then the sign, that is, are we getting the opposite sign of what we should? And the bias, are we getting usually positive overestimations or negatives? This is the how we are visualizing the results. Here is the variability. So very constant and then very stochastic. Here the duration, and in the color you can see the error. No, for example, in this case, the error in the growth rate. And as a threshold in white, we have put the 2% error per year. What it means that, for example, you can say that perhaps it's not much because 2% error is not, well, it can be acceptable. But then you can see that if we have an error, if we have a trend that is declining in a 2%, if we start with 100 individuals, only in 35 years, we get them to half. So it's something to take into account because we don't want to be wrong in a 2% because it's really misleading. So for example, here we can see if our simulated trend was this one. This is making a 2% error, and this is making a 5% error. Okay, so we really need to be in the blue zone. And this would be with all the autocorrelation. So here, perhaps it's a bit complicated to follow because then we will have more. But in general, we need to stay in the blue part in general and see how the white is changing with all the variables. So here we see that for negative autocorrelation, the trends in general are easier to find because the deviations are constant. It's like almost elasticity, more or less. And then that after 10 years to 40, and after 10 years, we're kind of okay in saying that our trend is the true one. With no autocorrelation, we depend much more on the stochasticity, and we need low values to get it right with long short-term trends. And with high autocorrelation, then we are misleading. Unless we have really low interannual variability, it's difficult to detect that, to say that something is right. These will be the results for the error, and these are for the false positive, for example. Here, it's a bit patchy because we are only taking the 0 trends, so it's not as beautiful as the other, but we can see in general that perhaps interannual variability and duration are not taking that much effort and are not playing that much effect in how many false positives we are finding. But autocorrelation has a huge importance. So as much autocorrelated are our data, we will have many false positives. For power, for example, we have said, okay, power is how much we are going to detect something that we have set it. No? So for example, we say, okay, let's see the probability to find the -2% decrease. That will be this one, a decrease like this. So slight decrease, kind of. So the probability, if we need to stay in the blue, the probability is really low. We need many years. And in this case, with high autocorrelation, it's almost impossible to find, to detect the 2% decrease per year. However, if we want to detect a 20% decrease per year, we are kind of okay in general. However, even the 3 years, this is 3 and 6 years, are misleading. So we might be getting a 20% decrease per year, which is a lot. It can be destroying a population in 10 years. And even if we have 6 years or 3 years, we will not detect it properly. These are other errors, and I won't go too much into detail into that, but this would be the violet will be that we are doing more positive bias than negative, and the brown would be the opposite. So we can see that for bias, we are doing more or less okay, excepting for the first years, where we have, in general, a bit more of a positive bias. That would be that instead of we have simulated this and we are finding consistently, we are finding something that is positive. For type S error, that is this one, type S error, I said before, is how many models are able to even change their sign, which is something very dangerous. It's not how much error we are making, it's that we are saying, okay, we have a decline, and actually it was a decrease, an increase, or the opposite. So it's something that should never happen. And in general, we can say that it's more or less okay. This is the probability of having less than 5% of type S error, of changing our sign. Still, high autocorrelation give us always some errors as soon as we increase the overdispersion. And the magnitude, we have, again, this is more or less the same pattern as we saw in the error of the trend, but in terms of magnitude. And the white is that we are going to find a 20% exaggeration only in our data, that will be the blue. And as soon as we get more or less here, this is finding 12 times the exaggeration of the real trend. So this is really saying something that is 5 times what we should been finding. Okay, so in this part, we see, okay, we might be in danger because things are not very optimistic. Let's look at how are the data on top. So where is the empirical data? Because this is simulated, but where are our data? So in the map, where are our models? So we took the information from the Biotime 2.0 that was released this last year by Dornelas, and we extracted the information for the time series for terrestrial animals, and we classified them into different different classes. And what we did, and what we obtained at the end, it was 16,000 models belonging to almost 3,000 species. And we, as before, we did the same methodology as before, obtaining, well, we ran the same models on all of them, and we extracted all of the time series characteristics that I said before. So here we have the duration, just this is intrinsic to the data. So we have like here we can see that birds, that is in this color, birds are intrinsically no, they are has been monitored for historically for longer periods. So we have a good, more or less a good duration. Insects, surprisingly as well, with a mean of 15 years, and the rest are really short term in general. For interannual variability, so how stochastic they are, we can see that for insects, in general, they are from 0 to 1. That is something that we were simulating before. And it's interesting to see that actually insects have a higher stochasticity compared to the other groups. It's something known, but it's good to see it on data. And then for autocorrelation, all of them more or less remain around 0, although we have positive autocorrelation mainly for birds and many negative autocorrelation. Each dot of this is one model. I don't know if I say. So this is the mean, and this is one of the models with extracted time characteristics. So then what we did, as you might be expecting, is to plot on top, like if it was a raster. So we plot on top each of the model and we extract the value that was beneath. And this is how, for example, the insects are in the surface map space. And this is how all the models look like when they are on top. And these are the means. But instead of visualizing it like this, that is a bit complex, we are going to visualize it in a box plot where below a certain threshold is where we are in the blue, we are okay. And then we have the percentage of models that are below the blue. So this is the result, for example, for the error. The probability of making a 2%, sorry, the number of models that are below a 2% error are those for all the groups. So we are quite okay for birds. That is almost more or less 60% of the models are estimating, have difference between this simulated error less than 2%. However, for the rest of the amount of safe models are really low. We did the same for all the errors that we have seen before. And we have here, again, to detect this slight decline that we have talked before is very difficult because those, for example, for amphibia and we just have birds that have more or less 20% of their models can be detected in this small decline, but the rest we cannot say. This shows that we cannot say whether these models are slightly declining or not. It's very difficult to find a power that is higher than an 80%. Then looking at the false positive, we have here the amount of models that have less of 5% false positive. So then we have, here is a bit more patchy. What we will have is that some of the amphibian arachnida are okay, so we don't find many false positive, However, for insects, for example, we have an 8% of the models that will not find, sorry, I said it the other way around. For insects, we have only 8% of the models that are safe in terms of the false positive. So this is quite, well, it's quite something, because we are seeing that our ability of relying on our data is doubtful. However, we can see that for type S error, we are kind of okay, because the models that are below the 5% type S error are more than 80%. So changing our sign is not as probable as other errors. Then for the bias, also 90% are more or less okay. We don't have an overestimation, constant overestimation or underestimation. So for type S and bias, more or less okay. And for type M, it's quite similar to the first error. So we will find, but it's a bit more optimistic actually than the other. So having a 20% exaggeration, less than a 20% exaggeration, is good for 75% of the birds, for example, or 40% of the insects. So here is a bit more the optimistic part of the errors. But in general, the key message of this would be that there is an important uncertainty in our overall trends, as you might suspect, and that we don't have power enough to detect these small changes in general. Even if we expand our time series, or we are in a need of increasing our power, or we cannot take conclusions out of small declines. We see that the too short to medium time series really produce misleading results. So getting back to the nature restoration law, how are we going to do if only 3 years of data are needed to reverse the decline? How are we going to trust those trends? Autocorrelation is, here we can see that the effect of negative autocorrelation is quite strong, and sorry, of positive autocorrelation, and also negative autocorrelation that happens a lot in nature is something that give us a bit more of space to safeness, we could say. And also that low stochasticity can assure more or less these robust trends. So if stochasticity is happening in nature because it is there, we can try to reduce the stochasticity with the monitoring framework that we are using. So reducing the noise we make while monitoring or sampling will make us be in the lower part of our map that we have seen before. And then the further steps that or what we recommend in general is, perhaps we have not tested this with GAMs, nonlinear models. This is just GLMs with Poisson distribution. Perhaps using environmental covariates will enhance a lot the models. Multiple taxa, aggregating taxa, will give us more of an idea of what is happening at the community level. And aggregating the plots, this we have tested it, and aggregating plots, for example, by 15 can reduce our error from 12 to 5, for example, 12% error per year to 5. So aggregating plots and information per plot, because the results I show was per species, but aggregating plots can be a solution to decrease the power. But we really need to look at our data, know how much error we can be doing, to then assess how to decrease our power in general. Okay, so after this, perhaps a bit pessimistic results, I will show something that is a bit more cool, almost. That is a near-term forecasting tool that has been developed in the Universidad Politécnica de Madrid, within the project we are in. And what they did, it was a package, a Python package that is called reservoir, that is a modeling framework that mimics a memory system. And what it does is to take environmental and biological conditions of the past to predict the future. And it uses temperature, wind, precipitation, soil moisture, and NDVI. It extracts all these depending on your geographic coordinates. Then it puts it in this black box, and then you get the result. And these are the results. This has been tested again with the biotime database. And here you can see, for example, this osmia that is fluctuating a lot, and all of a sudden, after 2015, all the abundance gets to zero. And the model that is the group, it's able to understand that everything will be zero afterwards, even though there was not this trend before, just here. So the model in this case was very good at predicting. The same here, it's not detecting this peak or outlier, but then the trend is more or less get for both correct. And in general, it's quite good at estimating the future. But it's not exactly right, this model. So what we did here is an insect forecasting challenge to test whether you or the algorithm that we have created is better than who is better in predicting, you or the algorithm, or the mean of all the users working that has gave an estimate. So it's an app, well, an app, a website that you can use in your phone or in the computer. And then you can display the temperature, the precipitation, the species information, and the geographic location. And then you have the trend has been fluctuating over the years. And then you have a blue point that you can track up and down. And then you say, okay, so this is for 2009. So 2009, we got temperature that is a bit below, and also precipitation. So perhaps the same characteristics in the 2000. So here, so I will estimate that the point is there. And then you submit it, and then it gives you the error you are making and what is the real trend and who was better, you or the model. And then you get estimate. So this will be what we did, and this is the average of other users, and this is the model. And in green is the real. So if you want to use it, it will be, I think you will be sent it, I think, next week if you want to use it. But it's good because we perhaps could see that the average can really reach the model, or the average of the users are more closer to the real data. So, and it's a bit like addictive or not, you will test it. And then you can see like, am I better? My predictability capacities are better than a model that uses EI, well, all the environmental data. So to finish, just some key messages. We have seen through these three edges that we have talked in the beginning that they are very complicated to accomplish. But we are getting there. We are making efforts. That from monitoring complement traditional approaches is key to reduce over stochasticity, but it's a complementation what is needed, not a substitution. And the identification by taxonomy is essential also to get to the species level and solve conflicts between species, between sites, between in the phylogenetic tree, etc. For modeling, 3 years, we have seen it's not enough. There is nothing else to say. And we need to keep investing in longer time series to get these estimates right. And accounting for these different statistical errors can give us complementary information. And for predicting, using environmental covariates can help us get a good resolution to the short term. So that's it. Thank you for being here and listening, and also all the people that have been working and helping and supporting, and long life to Tracy.
You. Really nice talk. Let's see if we have any question in the room or online.
Thank you for the talk. It was really interesting. So I'm wondering if I understand it correctly. When you simulate your models, your time series, you simulate the trend and the data, the error around it, right? And then you fit the model and see whether the model gives the right answer or not.
Yeah.
But that answer will depend a lot on the model you fit. So you hinted on a GLM Poisson, but maybe if you fit a model with a temporal autocorrelation structure and everything, maybe your prediction will be much better than with a simple GLM Poisson, whatever you.
Well, we account for
It's-
the correlation as well.
you know what I mean? Mhm.
So we have the autocorrelation, and we use GLM with Poisson because it's widely used, even it's just an estimate of what people are actually usually using.
Yeah, just playing reviewer too, he might say or she might say that it would be good to evaluate different model types and
Yeah.
model specifications in order to get that uncertainty right, because it's also a matter of uncertainty, right? It's not only the trend, but maybe you can, if you fit the really right structure, you can get the right uncertainty around it. And so that will play a big role in the results.
It's true, and we were planning perhaps to use the binomial models in a way, but it's difficult as well because we have to simulate, you have to get the simulation fitted for the model. So the simulations are to use a Poisson distribution, and then the autocorrelation also, and all the noises are simulated for that distribution. So getting another family would be, but we were planning to do it. I was going to say something. And that all the not convergent models and models that showed low R square were removed. So we have more or less control for random patterns. But yes, it's something we can talk about.
Okay, cool. Thanks. Questions?
Yeah, thank you. So what kind of information do you have about the factors provoking the observed fluctuations in insect abundance?
In the environmental, in the empiric data.
Yeah. Yeah.
We just have the how per study, we have how the study has been done, because we have from Biotime the study where it was that contributed to the database. So we have how the sampling was done. I guess that's the only source of uncertainty on the critical side.
Well, I'm saying that because I suspect that the reasons behind these fluctuations can be different every year, right? So it's not the same that the food is gone, a disease, something, when reproduction in the insect life cycle. So it's quite hard to model this kind of patterns when you ignore the reasons behind the fluctuations. So you said that one of the slides that you are going to include the environmental factors. I guess that you are trying to simulate the actual factors provoking the fluctuations.
Yeah, what we did, it was the last part out of. So in this part, it was just to do like what many people have done in insect insect bibliography. So just doing a GLM only for the abundance and the gear and the species. So this is like a warn of do not do this. And then it can be for sure complemented with environmental variables that will give us the information. And we can also see it in here as this, it's not exactly the same, but this is taking into account environmental variables and is able to predict quite good. So it's not that our method, we are proposing a method that is not good. It's just like the way it's usually done needs to account for other, it's a warn to use environmental covariance. But in our case, it's more, it would be more theoretical, I think, than testing what is, where the data are coming from, because the map is done without, it's just simulated.
Well, thank you for the talk. Sorry if the question doesn't make sense, because this is absolutely out of my field of knowledge. But I was thinking something related to Xavi's question. And this is about the differences in the error of the different models for the different taxa. I was wondering if you think that this variation is coming from I don't know, different sources like environmental heterogeneity, where the different species live, or the way that data was collected in different organisms. So maybe there is like some difficulties for collecting good data regarding like the biology of the different taxa. And if you have any like practical advice for improving this in the future, in addition to collecting more data during more years?
So I guess birds that show the lowest error in general are well understood in general, and they have been monitored historically for more than 60 years. So there is a long tradition. And then I think more or less we got the biology, we as biologists got the biology of the class birds quite good, and we are able to monitor it more or less. The environmental variables perhaps are not affecting them as much as insects, for example, but I also think that is the way we are collecting those data. Then, for example, for insects, it is clear that we are now starting to have long time series, long 15 years, and there was no tradition before. And also as I said, they are very dependent on the environmental variables, very dependent. And as devices, well, those devices can perhaps work, camera traps. I think the best thing is to have something that gets the whole gradient from night, within the whole day, within the whole season, as much data as you can without having just windows, but you will get the whole gradient, then you could understand better the data. And for Arachnida and other groups, I'm not an expert either in those groups, so we will have to. This is just we have just finished the statistics now, so we will have to look into it with more detail. If you have suggestions or something, we are open to it as well in general.
Okay, thank you. We don't have more questions or online.
Well, I just wanted to add to this discussion, because there is also papers by Nick Isaac showing that adding covariates helps you understand the patterns, and this is super valuable, but it rarely biases the estimate of the trend. So we can add covariates to understand better, and this is a goal in itself. But for all this policy that Julia was talking, like IUCN red lists, EU big directives, they just want to know the trend, and they are declining, whatever the reason is. So I think that's why it's relevant also to look it without this part of the biology. Yeah.
Yeah, that would be another postdoc, I guess. But it's very interesting. Just I think we could be thinking about those results for ages and taking conclusions because we have a long supplementary material of this. As you can imagine, like testing many things and could be added, be added with this how the uncertainty gets reduced with other covariates, but the trend still the same. But it is true that what Nacho said, in other cases, the R square of your model is better, but not the difference of the trend.
Okay.
Hi, Julia. Thanks for the talk. You said that mammals had a very low autocorrelation, temporal autocorrelation.
Yes.
I was surprised about that.
Yeah.
Like I was expecting completely the opposite, right? Like finding more like similar pattern to birds. And I was wondering whether you or the whole group have thought about whether this is actually true for these groups or populations, or it may be an artifact of our monitoring schemes. Like many of these groups have patchy distributions, so they might have a lot of extinction and rescue processes that we don't account for when you monitor one spot. Like you're not measuring the trends of the whole meta population that might be rescuing them in the next years, right?
Yeah.
Right. So whether evaluating, if this is the case, whether evaluating trends of all groups on these spots is actually representative of the whole groups.
Yeah,
Or
that's
just-
a good question, but it's really we were also surprised about first about patterns of negative autocorrelation that we were not expecting. We were just expecting either it's autocorrelated or it's random. But then this negative autocorrelation means, that what happened last year have a negative effect in next year. So it's like it's a bit hard to conceptually understand, but I don't know what it depends on for mammals, and I'm surprised that for insects gets exactly to zero, so it's like random, although the distribution is everywhere as well. But and then for mammals, it's really going down. Yeah, I don't know if we will. I don't know, because we are trying to follow perhaps whatever mammal or I don't know. I'm not also very familiar with mammal something, but in general, perhaps getting it in a certain point year by year to the same population is missing something that we are missing something that is happening there. But I'm not sure. That's the one.
Yeah, like for example, we can say what plastic plants budget here this year, and the other year is in this place 200 meters with something good. I don't know. Yeah, I just wanted to add to the debate on
Also, the amount of models for mammals, not quite, it's 140 compared to insect is 4,000. So perhaps we don't have enough data, or they are biased. You have to look at the species. Yeah, one idea at some point was to divide by kind of field, do the same, but just, for example, for butterfly, then for bees, then for, and same for mammals, and then see what is, are they all, are they segregated, or are they all over the place? So we could, that's why I say this can be studied for ages, because we could look at the species level, each of the species, the biology, or each of the guilds. A lot to think.
Okay, so thank you for your great talk and thanks for the interesting discussion also in the room. And we see you in 3 weeks because next week is Feria and next week is the discussion group. So thanks for coming and see you in 3 weeks.